Welcome to the 30th and the last lecture video for Physics 4A. We wrap up this semester covering mechanics. The first lecture video you will see is a semester recap, recapitulating the topics we have covered this semester, now reordered in the order of salience and importance, since we are no longer limited by the order in which prerequisite topics have to be introduced. After this first video, I have a few short clips from the class session in which I invited the students in the class to ask me questions they wanted clarifications on. The edited question and answer, especially containing conceptual and big picture advices that I think will also be helpful for students in other semesters, are now included in this set. Thank you so much for following our course content for the semester over the 30 lecture sets, adding up to more than 47 hours. I hope you will look at our course content for Physics 4B, which covers thermodynamics and electromagnetism. So let me do what I'm calling recap of the semester. And there's some value to doing a recap because when I'm covering topics initially, as we are going in a chronological order, because we are beings that live in a linear time and we only go in one direction in time. When we are covering topics that way, there's a certain order that I have to go in. I don't really have freedom of choice in skipping certain things, because as we are covering a certain topic, like for example momentum, certain things are presumed to be in your tool bag, and that puts a constraint that I think is not always most pedagogically sound, always most conducive to sound understanding of physics. And that's where I think the value of recap really is, because recap is a place where I can now ignore that order. I can reorder the topics, assuming you have seen them all, and kind of put the proper emphasis on the important things, just in the nature of how they are ordered, not just by amount of time is spent. So let me do that. Let me call this Physics 4A recap. Recap is, I think, short for recapitulation, but no one says that anymore. So let me recap what we have covered this semester. And the biggest thing I can say we covered this semester is really mechanics. This is the semester where you learn about mechanics. And there's a lot we can talk about, and a lot we did talk about mechanics. And I guess there's a phrase that I would encourage you to Google search, something called mechanical universe. It's a way of looking at the world. And I don't mean to say that, the material universe is the only universe, but the way we treat the world in physics and science in general is with this assumption of a mechanical universe, that all the phenomena we observe can be explained, can be planned, can be looked at mechanically, purely mechanically. And for anyone who's religious or spiritual, I'm in fact making no comments with regard to those non-mechanical realms. I'm just saying in science, we assume that everything that's relevant can be looked at mechanically. So that's our starting place. And as we consider mechanics, really the most important place that we started from, that you might remember, is Newton's laws. And Newton has many laws. We cover, in fact, 4 different laws of Newton. Newton's 3 laws of motion, first, second, and third law, and the Newton's law of universal gravitation. For the purpose of describing mechanics or the mechanical universe, what's important is Newton's 3 laws of motion. And even though we say there are 3 laws of motion, we do spend quite a bit of time with just one of them. And that's the Newton's second law. which says that net force is equal to mass times acceleration. This is the single most important thing that you learn to apply this semester. And this connects to another thing that we talked about towards the end of the semester when we were talking about oscillations. So the way the topics are ordered in the semester, they are quite far apart. Now, in this place of recap, I can put the proper emphasis just how closely related they are. So this is Newton's second law. And when we were discussing mathematics of oscillation, we talked about equation of motion. And the way we obtain equation of motion in context like oscillations is through Newton's second law. Because we start out with, okay, my net force is the force due to spring, which should be minus because it's a restoring force, opposite in direction, times the spring constant times the displacement. We'll just set the origin appropriately so that x equals 0 is equilibrium position. That's equal to mass times acceleration. And this is why we couldn't start the semester with the Newton's laws. We have to talk about the definition of acceleration, which is the time derivative of velocity, which is itself a time derivative of position. So double time derivative of position, you have mass times the second order time derivative of position. And this being put together, solve it for the highest order time derivative. This was our equation of motion, minus k over mx. So double. This was our equation of motion in the discussion of oscillations. And that's just an example of this application. So from this simple expression relating something that we call force, push or pull, to something that we call acceleration, or quantity that describes motion, we can get this differential equation. And from this differential equation, derive many properties of the system. This that's really mechanics. That's a good chunk of the semester is just wrapped up in that. So we have that, and there's Newton's third law, and there are other important foundational concepts we can attach to Newton's first law, something to do with definition of inertial reference frame. And but I think at this level of class it's not as important, so I'll just leave it for you to read on your own and move on. And in terms of Newton's third law, I think that's easier to talk about if I bring in our next topic of recap, which is dynamics. So we covered the Newton's laws, we covered the force analysis for some time, and then we had and then we introduced some new things that's not directly about Newton's law. And I would just summarize it as dynamics, which I guess let me not go too much into etymology, because trying to connect Greek words with the modern use of those terms is really it's fraught with pitfalls and false friends, false cognates. So, I mean, dynamics is words from the Greek word dynamos, meaning power, but like power is the least, and that has to do with Greek use of the word power is not how we use the word power. So let me just forget about the Greek etymology and just talk about what dynamics is. And dynamics is, I guess, there are two pillars of dynamics. It's the energy and momentum. These are what some people call twin pillars of classical physics, or twin pillars of conservation laws, conservation of energy and momentum. And we introduced the problem-solving strategies that use them. And so these are the two most meaningful quantities in dynamics. And momentum connects directly to one of the laws of Newton's laws of motion. So momentum is the quantity that most closely related to, relevant with Newton's third law of motion. And recall back in the lecture how we treated conservation of energy and conservation of momentum. And they were really heaven and earth. They were that different. With the energy, we started out with the assertion that energy is conserved. And really everything we have done since then, such as defining things like work, we define the work as force times force dot product with the displacement as a way to come up with a quantity that would be conserved through different mechanical interactions. And from this definition of work, we derived the formula for kinetic energy as 1/2 mv squared, and we derived some formulas for potential energy. They all came from this relationship that potential energy is the negative of the work done by conservative force. And all these quantities we introduced, defined, built up, they were designed to do this one thing, that there's this one conserved quantity that we are going to call energy. Energy is it's a computed quantity. It doesn't I guess one way to say it glibly would be, if we never defined energy, dynamics would stay the way it is. Like us not introducing the idea of energy wouldn't change the dynamics itself. But this is such a useful problem-solving tool that that we treat this as being something real. And there are real effects that do come with energy, like when some of the mechanical energy turns into thermal energy, we feel that as a heat as things warm up, and it feels different. So but at its core, energy is a calculated quantity that's calculated and related to many different things by the way we treat it. Momentum, I call the way we treat conservation of energy momentum heaven and earth, because how we got conservation of momentum is different. It's not a second quantity that we somehow designed that we should also conserve in addition to energy. Conservation of momentum comes straight out of Newton's laws, from Newton's third law, which says that if an object A exerts a force on object B, then there's a counter force by object B on object A that's equal in magnitude and opposite in direction. That's Newton's third law. And conservation of momentum is a direct consequence of that Newton's third law. And we do introduce some quantities like impulse that helps us express this. Impulse is defined as a force times duration of time, and this duration of time being duration of interaction. So the duration of interaction with the two interacting bodies is the same between them. It's kind of symmetric that way. You can't have one that's exerting force on the other, while this is not because of Newton's third law. So with this introduction of the concept of impulse, we can express the quantities that relate to change of momentum more succinctly, and we see that if you only have internal forces, which depends on how you define your system, and the most important thing about internal force is that when you analyze the interaction between the two bodies, both the action force and the reaction force, they are in your system. So that as you look at the total change of the total momentum, that if all the forces involved are force between the objects in your system, then those action reaction force pairs will result in impulse that's going to cancel each other out within the system. Now, once you have external systems, once you have other objects that you are not tracking, then conservation of momentum of that system is not that's not held, but that's only because it's getting momentum transfer from outside the system, or from or to the other outside the system. And as you look at this two different aspects of dynamics, energy and momentum, that there's a lot of similarity and differences that you need to watch out for. I guess the biggest thing is energy is scalar and momentum is vector. So the kind of in this class we shelter you a little bit because we deal with the momentum in 1D so that you only have to worry about positive and minus. But those pluses and minuses, they are not talking about increase and decrease. They are talking about direction. And in more generally, you have to think about momentum in 3D. So we covered Newton's laws, we covered the dynamics as we were introducing and teaching mechanics, and I think that's it. I think that's all the mechanics we've covered. I mean, I don't mean to say that's everything we've covered. This is only like 4 weeks of the semester, but these are the fundamental concepts. Everything else we do in the class, they came from these fundamental things that we covered in these 4 weeks or so. The rest are either applications or prerequisite mathematical content. So I don't know if I remember all the applications. Let me try to let me give it a try. Let me try to remember all the applications of mechanics. So what things did we apply these to? I guess the biggest thing where it's also maybe a little bit controversial that I'm calling it application, not a mechanical topic on its own, is the idea of rotation. So rotation was an application of these mechanical concepts. And the biggest reason I have for calling rotation an application is because in classical physics, basically there's no concept or no quantity in rotational motion that you can't derive from some translational motion, some linear motion. And be careful here, I said classical physics. For some of you, when you take a quantum mechanics later, you will see that there are quantities in quantum mechanics that relate somehow to rotation that don't come from translational motion. So as we go from classical physics to quantum mechanics, at some point rotation will be its own topic of mechanics. The quantum mechanical angular momentum is a really important quantity that governs many different interactions in physics and chemistry. And I want to draw a distinction there because when we introduce that quantum mechanical angular momentum, that'll be something new. That's nothing like what we've been talking about, other than by analogy. So I want to draw a clear distinction here that what we are covering now is just an application of mechanics. So in fact, the place where it's kind of the easiest to see it is the analogs. By analogs, I mean things like, so in the translational motion, we had a mass. And in the rotational motion, we introduced rotational inertia. And in the lecture, we went through the whole derivation of that. And in the translational motion, we had the velocity or speed. And in rotational motion, we had the angular velocity or angular speed. And we went through derivation of how it relates. And once you introduce all these different quantities that are analogous in the two different motions, then you can build up expressions in the rotational motion that are completely analogous to the equations that you had in translational motion. So for example, in translational motion, we had the momentum, which was mass times velocity. And in the rotational motion, we have angular momentum, which it's not the definition, but oftentimes it can be described as angular rotational inertia times angular velocity. And we had a kinetic energy, which was 1/2 mv squared. And there's a rotational kinetic energy, which is 1/2 rotational inertia times angular velocity squared. Notice how these translational quantities are being replaced with the rotational quantities. That's what we mean by analogs, that this rotational dynamics is built up in such a way that we can rely on relationships like this. That's one of the things that should tell you, oh, it's an application of dynamics in the translational setting. And so within the rotation, let me pull out angular momentum as its own thing. We did look at some examples where angular momentum helps explain some really counterintuitive motion, like a precession. So I think it's worth pulling out as its own separate application. Let me just name precession. But even here, we can understand it through the same way we understand linear motion quantity. So in linear motion, change in momentum is force times the duration of time. That's what we talked about way here. And if kind of analogizing it to the rotational motion, we can say that the change in angular momentum, it's a vector, is equal to the torque times the duration of time. And this vector aspect gets quite complicated, which is how you get that wonderful counterintuitive precession motion. But it's still just an application of what we've learned in translational dynamics. And and what we ended with was static equilibrium. Static equilibrium isn't really even rotation because we're talking about when things are static, but I guess it belongs in that category because you need a torque to talk about static equilibrium and still application. And then I think we had other things that are more, no one would dispute with me. As I say, they are applications of mechanics, things like oscillation. We covered oscillation, waves, and these are quite obviously application of mechanics. It's a particular, you can almost look at it as a case study. You have a particular scenario, you have some defining parameters of the scenario, and to that scenario, we apply what we learned about mechanics. We apply what we learned about forces and things like equation of motion. And we apply things like energy and maybe not so much momentum, I think. So energy. And both of these are wonderful, wide-ranging applications of mechanical phenomena. And finally, this is another thing. I'm gonna put it under application of mechanics, but I recognize not everyone would agree with me. Fluid dynamics. And I call this also application of mechanics because in covering fluid dynamics, we didn't have to introduce any new mechanical quantity. I mean, we did have to define some new way of treating things, like we defined the pressure as a force per area. We defined the density as a mass per volume. But this was more of a different way of dividing up things so that you can create a little fluid element. But once you have that fluid element and you're treating that motion of that fluid element, then it's just the mechanics that we learned before. So fluid dynamics is another application of mechanics. And that's really what we spent the other half of the wait, that's not quite enough. I know what I forgot. So we spent the time covering mechanics and application of mechanics, and we spent time covering time on prerequisites or mathematical ideas. I mean, let me put it in quotation because it's not really it's not prerequisite like a prerequisite course. It's a prerequisite in that it's the things that you need to know. So that's why we covered it. But at its very core, it's not really physics because in talking about these things, we didn't introduce any physical ideas. And the biggest of this is kinematics. I used to half joke when we get to Newton's laws, which is about fourth week in the semester, that we are finally covering physics. And I say half joking because it's true. When we do kinematics, we are talking about the position as a function of time. We are talking about velocity as a function of time, and acceleration as a function of time. And velocity is defined as the time derivative position. Acceleration is defined as the time derivative velocity. There's not a single physical idea here. I mean, it's really a mathematical description of a particle moving about. That's really all that is. And, we did talk about certain problem solving approaches, but at its very core, kinematics is just math. The reason, and it's the very first thing we covered this semester, and the reason we had to is because we needed you to understand what acceleration is for us to talk about Newton's second law without a preconceived or notion or something we teach about acceleration. Newton's second law makes no sense. And this is what I mean. When we are first covering the topics, we are forced to go in specific order. So the whole kinematics formulas, that's not what physics is about. That's just mathematical problem solving, which is important, but that's not what physics is about. But you do need that as a basis so that you have some intuitive sense of what acceleration is. So that as we use acceleration in the description of our laws, that it makes sense to you. So yeah, we had that mathematical prerequisite. And I feel like I forgot. Oh, you know what? Newton's law of universal gravitation. It's a fourth law of Newton, and I think I would actually. Oh, where would it fit? Let me put it this way. I'm gonna create a new category just for it, and I'm going to call it laws of physics. And my contention here is that we taught you exactly one law of physics this entire semester. And it's Newton's law of universal gravitation, that the force between two objects, m1 and two masses, that there's an attractive force between them, and the magnitude of that attractive force is given by some constant, or I guess the way Newton formulated it would be proportional to product of the masses and inversely proportional to the distance squared between them. And the g is the constant of proportionality so that we can make this equality. I'm telling you that this is the only law of physics we've taught you, because the Newton's laws of motion, it's not. I guess it's a question of what you consider to be laws. So how do I let me give this a bit of a thought how I should phrase it. This is the philosophical question that you might consider, which is, how do you define a force? I mean, I did give the whole types of force lecture. I do have some sense of what force looks like. We call it push or pull. And you might say, oh, it's so intuitive. Yeah, push or pull. That's how you define a force. When something pushes or pulls, then we say that's a force. Then the question might be, how do you know something is pushed or pulled? When you have a contact force, then maybe it's so obvious that it doesn't need an explanation. No more than, typical math class, you'd hear an explanation of why 1 plus 1 is equal to 2. It's so obvious that it doesn't need an explanation. Another way to say this, it's axiomatic, it's foundational. It is our starting point. And in math, when we talk about axioms are not something you prove. It's something you assume. Because when you do your proof argument, you have to start from some place. And that place that you start from, there might be a more fundamental things you can prove that starting place from, but you can imagine keep going further. So what's the most fundamental thing? And at some point, you hit bedrock. You hit bedrock of assumptions, things that can't be proven from anything else, or anything else that can be proven from other things. And Newton's laws of motion are like those axioms in mechanics. It's our starting place. Newton's laws define force for us, so that when we see forces like a gravitational force, which is not a contact force, we don't see it literally grabbing onto something and then pulling. Like, we don't see that, but we call it force because it causes acceleration. From the fact that gravitational force causes acceleration, we call it force. And then you might say, that sounds circular. And yeah, it is. And that's why I'm saying Newton's law of universal gravitation is the only proper law of physics we've taught you. Because everything else is either mathematical prerequisite, things you have to know to do quantitative problem solving, or kind of definitional concepts in mechanics. Even though we are calling it laws, it's not empirical law. It's not law like you do an experiment to verify their truth of. Newton's law of motion defines dynamical quantities for you, so that you can further define other dynamical quantities that we have introduced. And so this semester, we really spend all of our time doing that, all of our time developing those mechanical concepts, which means we didn't have a lot of time to teach you real fundamental laws of physics, other than this one, Newton's law of universal gravitation. This is the one fundamental law of physics that we've taught you. Oh, there's also Hooke's law, but that's not fundamental. It's just kind of phenomenological description of spring force. So that's also not a real law. So yeah, this is a recap of the whole semester, which is the semester which is really about mechanics. That's what this entire semester is about. And we've developed quite a bit of tools, and these are all important tools as we further your study of physics. Actually, physics of 4B and physics of 4C will teach you many laws of physics. It's just that you needed the tools that we teach you in this class in order to make a sense of those laws as a physicist, as a scientist, as an engineer can. or should be able to. So we spent a lot of time introducing these things that are not laws of nature, just how we choose to analyze nature as a mechanical universe. And we've given you some applications of these principles, and we taught you one law of physics, Newton's law of universal gravitation. That is the one law of physics that we've taught you, which you can't do anything with except by using these principles. So yeah, that's the recap of the semester. Let me know of any questions.
Questions on problems?
There's one question about the thing with the density of like a rod and finding the rotational inertial.
So that was for exam 2, I think. Yeah. And let me just highlight the parts of the solution that I think everyone here can get. It's a more matter of concept, not working through the algebra or calculus. So this is a key step you need. So let me highlight this. And I will tell you why that's the key step and how to sort of get to writing this down and what you do once you write this down. So what does this expression express? What does it say? It's an equation that's a kind of a sentence. What does this sentence say? What does the left-hand side represent? It's not a derivative. It's a differential maybe, but I'm not asking you what is the mathematical form. You could have said the left-hand side is di. What is di? So what kind of physical quantity is it representing on the left-hand side? Moment of inertia? Yeah, moment of inertia or rotational inertia. So this is saying, all right, rotational inertia is equal to something. What's on the right-hand side? What does dm stand for? What kind of physical quantity does it stand for? Mass, right? Standing for some kind of mass. And what does, so this d, it stands for distance. So the sentence that this equation is saying is that rotational inertia is equal to mass times distance squared. That sounds right. In fact, it sounds right for a very specific case. It's correct for a point mass. When you have a point mass in space and you want to know its rotational inertia about a particular axis, then all you need is its mass, the distance, then mass times the distance squared is the rotation inertia as it rotates about this point. So that's what this expression is saying. Now, so if that's only true for point mass, why are we saying it? We are not dealing with the point mass here. So that's the front part that you need to handle. And for each of these, this symbol D, it's not a derivative, but it does stand for some kind of meaning. It does have a meaning. And the meaning that I want you to remember is infinitesimal. These D's stand for something that's infinitesimal. Everyone here knows the meaning of infinitesimal? It's like the opposite of infinite. It means very, very small. So what this is saying is the very, very small fraction of rotational inertia, we can express it as a very, very small fraction of mass times the distance that mass is at squared. So to express this mathematically, that's where you need this picture. You have this extended body, which is not a point mass, and you couldn't have expressed it as point mass. But what you do is you say, I'm going to break it up into tiny little pieces. So I'm going to imagine breaking it up into very small pieces. Say that this piece has size dx. And like that other d's there, this d stands for small. So very small portion of x. So when you take that small portion, it's going to have some amount of mass dm. And for this very small portion of the object, we can say that this contributes rotation inertia di to the whole thing. So that's the conceptual step you need to go through. This is something that your math class wouldn't, your calculus class wouldn't have covered. Because in your calculus class, what you would have is you'll be given this and asked you to do the integral. In this class, the actually more important step is getting to the expression that you are going to integrate. So this is the starting point for a problem like this. And you need to have a diagram drawn. And in this diagram, have a sense of what each of this di, dm, and the distance stands for. So here, once you draw the diagram, that you see that this is my center of rotation. And this whole thing is the distance, not just the x or any old symbol representing position. Yeah. So this is the important first half, breaking up your extended body into small enough pieces that you can use, you can treat it like a point mass. Then the next step that's also important, the second half, for the start of the second half is this expression here. So this is more symbolic than anything. It's just saying total rotation inertia is that infinitesimal rotation inertia added all over the entire object. And the really important step is essentially this portion. And this, and this. You have to know what you are integrating with respect to. It's easy to say, I'm going to integrate over this car. All right? Tell me how you are going to do it. Tell me nuts and bolts, the exact detail of how you are going to integrate over the car. And in this case, what we've said is we are going to parameterize it by position. So we are going to add up this quantity by adding it with respect to position, like a position at y equals 0 to y equals the length. So this dx tells you the variable of integration. That's the parameter you are using to express all the different parts of the object. And the thing that's coupled with this are the limits. X goes from 0 to the height, goes from 0 to the height. So the very first line here it's just a symbolic reminder that I'm going to integrate over this physical object. But that doesn't really tell you how you are going to do it. The second line is the detailed expression of how we are integrating over the bar. We are doing it with x as the parameter, and that x changes from 0 to h. And the rest of the expression here is written in a way that it supports this. dm is written in terms of, I guess we did it here. dm is written in terms of x by using density, and distance is expressed in terms of x by considering the geometry and figuring out the relationship. Yeah. So I can imagine, probably not something complicated like this, but for something simpler, I can imagine asking people to set up the integral. In fact, the reason I focused so much on this for your exam too was this is a model of how you do approach a lot of similar situations in physics 4b and actually physics 4c. This is a situation where you know how to handle a very simple case. You have a point mass, you know the formulas for it, but now you want to deal with something that's extended, some bigger object that you don't know how to deal with. And the approach is you break it down, and then you calculate the effect of that small portion, and then add it all up. No. We actually did that with the energy too. We did it with the spring potential energy. And if we had time, we could have done it with the gravitational potential energy. And all those are following the same general idea. You take the whole interval that you don't know what the answer to is. You break it up into very tiny pieces. Each piece you can handle. And then Using that, set up the integral, and the final integration is where, from knowing this small portion, now I know how to handle the big part. So I don't know. I haven't written a cumulative final exam, so I don't want to promise anything. But I'll just say this much, that this is something that I felt, after teaching this class for a while, this is something that I felt everyone going through this class should know how to do to prepare yourself well for Physics 4B. So. Okay, any other questions, either on the midterm or, we still have like 20 minutes. Yeah?
15 example.
Same exam? Yeah. Okay, let me scroll to 15. Was? Okay, 15 was one of your homework questions. That should have been easy, right? Maybe not. I mean, so yes, it was in the homework. For those of you who actually did the homework question and read it through the explanation, then you should have been able to do it. But yeah, this is a new, I guess I would say this is difficult. One, because it's new. This is not one of my reused question. I wrote it new for this semester. And two, the kind of reasoning you had to do for the homework question, it's not something we emphasized in lecture. So it's a type of reasoning that you haven't seen before. So I guess here's one way to do it. It's to, it's not really the proper way, but it's the way a lot of times a physicist does things. Let me just show it to you as a particular way of thinking about things. We call it abusing the notation. So when you're abusing the notation, it's important that you label the things carefully before you start abusing the notation. I'm not sure if it's an actually abuse. I feel like I'm abusing something. So let me express three different variables. There's variable y indicating position along the vertical axis. And there's the variable x indicating position along the x-axis, right? And there's the variable time, which represents t, which represents time, which is not represented anywhere on the axis. This is a snapshot. Time is represented by letting time flow. And when you let time flow, this kind of moves across, right? All right, so the question is asking, what is the vertical speed of the point A? So it's asking, all right, it's asking for this particular combination of variables. It's asking for dy dt, right? Now, you are not given dy dt anywhere. This thing that you are given wave is moving to the right with the speed 1.0 meters per second. How would you express this in terms of symbols of these dynamic quantities that you have? Like the wave speed. Is it described like how fast the y is changing or how fast the x is changing? How fast the x is changing, right? Kind of in a very roundabout way because no object is moving that way, but the shape is moving that way. But whatever it is, so this is describing dx dt, speed along the x direction. So you're trying to somehow get from dx dt to dy dt. So I stare at it for a while, and I realize all I need to do is cancel out dx and put dy in that place. So the way I can do it is by multiplying it by dy dx. Then, dx will cancel out, and I'll get dy. I call it, so it's called abusing the notation because that's not how it works. But how it actually works is chain rule. So what you have is y can be expressed as a function of x, which itself is a function of time. So when you take the derivative of this with respect to time, then using the chain rule, you would get, derivative of this with respect to time is equal to derivative of this, dy dx, and then derivative of the inside, dx dt, right? That's how it properly works, but this is a quicker way to get to the same answer anyway. Kind of pretending that dx's cancel out, which they don't, but I mean, we're not in a math class. So that's the relationship that's written down here. dy dt is equal to the rate at which the wave is moving, or I guess I flipped it around. Well, I'll put it there. Rate at which wave is moving times the slope, dy dx. dy dx. And the proper way to understand where this comes from is through the chain rule. But if you thought they worked out by these two things canceling out, it's not wrong. It's sloppy, but it's not wrong. So realizing this is the biggest part. Once you do that, then the rest is easy. You can estimate the slope of this point by drawing the line, and you get slope as approximately, for 1 centimeter of rise, it moves across by about 10 centimeters or so within order of magnitude. So that's the slope. So slope times the wave speed gives you a tenth of a meter per second, or 10 centimeters per second. That's what the answer is. Okay. So, I don't know how much I would focus on question like this. This is one of those things where I'm essentially testing you on trivia. And I do want you to still have the goal. If you were to see the same question again, you wouldn't miss it a second time. But the nature of a trivia question is that there are so many trivia questions. You may not see the same trivia question twice. So, yeah, I don't know. I'll have to see. Yeah?
Angular momentum.
Yeah, angular momentum. Which part about angular momentum?
Like the interaction between torque and angular momentum causing change in motion.
Yeah, so let me bring out my demo for that. So you remember the bicycle wheel, right? So there's different levels at which this question can be asked. And angular momentum is a topic that will probably occur on the exam. So it's worthwhile making sure you are familiar. Now, the one example you have seen dealing with precession, that's the level at which it's the most difficult. Because with the precession, that's where you have to bring in cross product. You have to think of angular momentum as not just counterclockwise or clockwise rotation, but as a vector that's using the right-hand rule, as a vector that's pointing towards you. And it's a very abstract way of thinking, and it's not easy. That's why I want to bring this other level that I think actually everyone can get. Because in this particular case, we can say this. Instead of trying to think of angular momentum in 3 dimensions, you can say, I'm going to restrict myself to looking at rotation in the horizontal plane. So that if you see something that's rotating like this, you say, well, viewed from above, it's not rotating. Right? And you only consider the rotations that you can see as you are looking at it from top. So what it is you are limiting your angular momentum or any other rotational quantity along the z-axis alone. Because anything that's rotating in the horizontal plane will have component of the cross product stuff along this axis. So I think that's something that everyone can understand, because then you are limiting yourself to one plane. You are limiting yourself from one point of view, and say from that point of view, it's clockwise or counterclockwise. And this is a demo you have seen where right now, viewed from above, nothing is rotating. And even when I do this, viewed from above, nothing is still rotating, because this is not rotating in the horizontal plane. So what you can now say is that angular momentum of the combined system is 0 as viewed from top, or the component along the x-axis is 0. So when I flip this around so that viewed from top, the wheel spins clockwise, then this is where I use conservation of angular momentum to say, oh, the net angular momentum between the, together with the wheel and me should be 0. Wheel is spinning clockwise. That's why I'm spinning counterclockwise. Right? Oh, and it's until the friction kicks in enough so that it doesn't. All right. Let me try to stop myself here. So you can understand that in terms of conservation of angular momentum. And if you want to go a little bit more into it, why angular momentum along the z-axis is conserved? Well, I'm on this rotating platform, so there's no external torque on me that's along the horizontal plane. Any torque on me would be not around the z-axis, but around the x or y-axis. As in, like if I try to do cartwheel like this, then I'm applying a torque along around this axis. Does this address your question about angular momentum? The other thing about angular momentum that is challenging is remembering all the different relationships. In fact, this is the biggest challenge with rotational quantities. And I mean, it's actually biggest challenges with physics. So it goes with what I was saying about how you approach physics is different from how you have approached other science classes. Like when you're taking chemistry and when you are doing gas laws, you had to know ideal gas law, and that was it. There was really nothing else you had to know. A lot of the questions that you might be asked are essentially application of ideal gas law. When you do thermodynamics in physics, it'll be a little bit challenging because using ideal gas law is only a first step. You have to know a bunch of other stuff to work out whatever question we are asking. The requirement is in physics is that you don't know quite as many wide range of topics as you might in other subjects. Like, if you take human anatomy, you're going to know a lot more about human bones than I ever know. But that narrower range of topics in physics comes with a level of focus. That those narrow range of things you know them very, very well. So a lot of people, when you study something, you find out something, and then you think to yourself, oh, that's enough to know, now I move on. And that's not right way to study physics. That's why we emphasize problem solving, because it's when you're solving problems that you realize, oh, I need to know all these other relationships also to solve this problem. So with the angular momentum, these are all the formulas involving angular momentum that you should know. And you should know like which one to use when. So let me write them all down so that you see all of them in one place. So let me start out with the version of angular momentum. That's the definition of angular momentum. Or at least, yeah, it's the way it's most fundamentally defined. So angular momentum is defined in terms of the translational quantities, momentum and displacement. It's a displacement cross product with momentum. That is the definition of angular momentum. It's the definition of angular momentum you can apply when, like if this is my axis, and if I have a point mass that's moving across a constant speed, this actually has angular momentum about this point. In some sense, this is rotating about this point. It's kind of going in from your view, it's going in a clockwise direction, right? The radius is changing, but throughout all that, it's kind of going in a clockwise direction. And in fact, if you apply this, you'll find that as this passes through, its angular momentum is constant because the lever arm doesn't change. So this is the very basic definition of angular momentum. And if you're dealing with not a point mass, but an extended body like the bicycle wheel, then you would go through the procedure that we are describing. Imagine breaking this up into tiny little masses, and you integrate it over the whole, integrate the tiny little contribution to angular momentum, and add it up over the entire object, and you get the total angular momentum. So a result of that can be expressed this way. Now, this equation is not always true. You can find exceptions to it, but it's true often enough. So this is the expression. Angular momentum is equal to rotational inertia. So for rigid body rotation, this is where all the hard work has already been done for you. Because in figuring out the rotational inertia of the object, all that integration that I was describing was already done. So that rotation inertia times the angular velocity, omega. And this is the formula that will remind you of its translational analog. the translational analog of this was momentum is equal to mass times velocity. Right? Yeah. So, so this is another expression for angular momentum that you might use in some situations. I will warn you that this is not always true. This is true only when you are rotating about something called the principal axis. This is something you can read about in the textbook. I will tell you this much. I will never give you a rotation of a rigid body that's not about a principal axis. Because, I think it's actually about an axis that's parallel to principal axis. Whatever. I'm never going to give you a situation where this is not true. But as you go on to do your job as an engineer or whatever, you should know that this has exceptions. That's when you fall back on this. So that it's just not so abstract. The exception comes with this. So if I take this wheel and rotate it about this, or if I even rotate it about like in this way, all of that's fine. But if I try to mix it up, if I try to rotate it like this about this axis, then this will start to develop some kind of instability because of the fact that this is not true anymore. So read about it in the textbook. So we have written down two. We are not done. There's one more relationship for angular momentum that will sometimes be useful. And that's this one, the relationship between angular momentum and torque. As in, I guess it's easier writing it the other way. Torque is equal to rate of change of angular momentum. Or if you really want to write down angular momentum, it would be change in angular momentum is the time integral of torque from some time equals 0 to some final time. Right? So this is the third relationship that involves angular momentum. And you can maybe see how this relates to this by remembering that force is rate of change of momentum. So this together with this does give you something like this. But so angular momentum, just a single quantity. There are three different expressions that deal with the angular momentum, and a given particular problem will be easier to handle using one of these three, or two of these three. But so this is what I want to caution you against. If this is all you know about angular momentum, there will be questions that stump you. If this is all you know about angular momentum, there will be questions that stump you. If this is all you know about angular momentum, there will be questions that stump you. In order to be able to do all the questions involving angular momentum, you have to know all three. And you have to have some level of familiarity on which one is more appropriate. But a good starting place is knowing that there's these three different expressions. Then you can do trial and error. You try one. If you seem stuck and not going anywhere, you try the other expression. If it doesn't work, you try the other one. But you need to know what to try. Okay? So this is an example using angular momentum, but almost all the rotational quantities can at least be expressed in two different ways. And it's important to know those at least two different ways.